All right. The formal name for the second idea that we're covering is reduced resource computation. That is to say, do more with less. But more realistically, I would say something like trading accuracy for time. So you could use a 32-bit floating point number, F32 or float, instead of a 64-bit floating point number, F64 or double. And you are giving up some precision on that, and you are potentially losing a little bit of accuracy, but also, since the 32-bit floating point number is smaller than the 64-bit one, it's possible to fit more of them in the same amount of memory, and perhaps possible for your 64-bit CPU to work on more than one of them at a time. That sort of thing could actually prove to be a significant benefit in terms of actually doing the computations. You could also work with integers representing floating point numbers, where you say, all right, instead of having a floating point with a decimal place where we represent, okay, the part before the decimal place is the dollars and the part afterward is the cents, you could say actually just represent everything as an integer number of cents. But we have to think a little bit about situations in which this is appropriate. So here's an example: circuit analysis. Let's not get too caught up in circuits as a topic, because this isn't a circuits course, but it's a good example of where we are trying to do a simulation, and the simulation is going to have some precision, but not infinite. And when you do a scientific computation, you are entering points that were measured with some error, and they're computed using machine numbers, which also themselves have some error. There are numbers that cannot be easily represented in binary because they require an infinite number of digits to represent. And that kind of thing introduces a little tiny bit of error, and you probably learned in a concepts course long ago about measurement error. And that kind of thing enters into our thinking here. What we're interested in is our simulation good enough? If the goal is to do some circuit analysis to figure out what resistors you want to put on your circuit board, is there any point in calculating down to 5 decimal places what the exact resistance should be when the resistors you buy have a tolerance of plus minus 5% or plus minus 1%? No, and if you took a circuits course with Professor Barbie, he will be very disappointed if you said yes. The details don't matter at that point. It doesn't matter what the 4th decimal place is and the 5th decimal place is for calculating this resistance when you're buying components that have 1% tolerance. It's silly. It's not helpful. You're wasting time, and you don't want to make them look like this, do you? Okay. Perhaps my favorite example of trading some accuracy for time comes from the source code of Quake 3, in that there is a function, the fast inverse square root. And without boring you with the graphics details, for graphics processing, sometimes you want to calculate 1 over square root of x. This is used for calculating lighting and reflections because you need to normalize some vectors. Normalizing is mostly a straightforward exercise. You square some numbers, you add them up, and then, oh no, you have to use square root. Square root isn't actually that simple. Square root is usually calculated by interpolation or root finding. If you took a numerical methods course, you know about how to do that kind of root finding method, do Newton's method or something similar, and that is going to take a variable number of steps. Squaring things is straightforward. You just multiply a thing by itself. Adding is straightforward, but finding a square root is usually slower than that, because you have to do some number of iterations, and how many iterations are we going to do? And it's not that fast. And here is the original code for fast inverse square root. There's a bad word on the slide. Oh no, clutch your pearls, retire to your fainting couch. Here's what it does. Given a float x, it calculates x half as 0.5 as a floating point number times x. Fine, sure, whatever. And then cast address x to int star and dereference it, and then take this constant of hex 5f3759df minus and then I bit shift 1, and then turn it back into a float. And then x is multiplied by 1.5f minus x half times x squared, and return x. What? This is like really dark magic. The first line, take half the value of x, sure, easy, great, no problem. The second one, interpret the floating point value as an integer. What? I mean, you can, but why does this make sense? If you look in the linked source in the notes, it will go into some details about the math and proving all of that. But what it really comes down to is, how is the float stored? Effectively, the float starts with a sign bit, then the exponent, then the mantissa. If you need a math reminder, 1.95 times 10 to the power of 3, the exponent is 3 and the mantissa is 1.95. With that said, the clever hack is super neat, but is actually kind of obsoleted now that CPU instructions offer you a fast inverse square root. That instruction was not something you could rely on in 1999, although some CPUs had it at that point, not all of them did. We'll revisit the idea of using CPU instructions very cleverly in an upcoming lecture. But if you say, look, just pretend this floating point number is an integer, we end up with something that looks like this. So given a floating point number, turn it into an integer with like a direct cast, the kind where you say, C, I want you to interpret those bytes of memory as if they are an integer, not any sort of actual conversion. Does that graph look like anything to you? Well, the plot of it rather resembles the plot of -1 over square root of x. So we're actually pretty close to where we need to be. We are going to convert it, so we're going to invert it. And the seemingly magic number of 5F3759DF is not a bit pattern, but it's actually just a calculated offset to make the approximation a little bit better. Okay. We said interpret it as an int, and then use this offset to shift our approximation a little bit. It's not any bitwise cleverness at this stage. And then turn it back into a float. And then do one quick iteration of Newton's method to refine the calculation. So this step here where we do x times 1.5f minus x half times x squared is one quick iteration of Newton's method. And we end up with something like a reasonable look at this function. It is fast. It is constant time, which is also important, and it's very accurate, something like 0.175% error at most. And in a 3D game, a tiny inaccuracy is not a big deal, especially a game from 1999. It was not exactly photorealistic to begin with. Now, was it? Now, this is the best case scenario because the accuracy that we're training for speed is very small, and its application is one in which we don't actually notice that there's a small difference. This is actually even better than just close enough is good enough. This is hardly any trade-off at all. This is totally worth doing. All right, next application then, a common physics problem that programmers are asked to simulate is the Endbody problem. At one time, this was an assignment in this course for using GPU. There were too many good solutions on the internet, so we had to replace it, but it remains an interesting parallelizable problem. But anyway, the Endbody problem is you have some number of bodies, n, given a simulation, and they interact via gravitational forces. And the program needs to compute the movements of these bodies over time. And this is a great example of a very easily parallelized problem because you can compute the forces on each body n from all other bodies in parallel, and there aren't really a lot of dependencies on them. While you're computing one step of the simulation, you are saying, all right, it happens in such a short time frame that every point is not moving, and we can just calculate it. What is our next step? And then you go on to calculating future steps. Okay. So, I mean, what could you do to speed this up? In the theme of trading accuracy for performance, there are a few things that we could do. And one of them is using float instead of double. Again, that reduces the amount of storage and therefore reduces some of your costs for shuffling data around at potentially the cost of a little less accuracy in the tiny decimal places. If your goal is you need a super precise scientific computation, then you might not want to do that. But if you're just rendering, a nice background or a game or something like that, a little trade-off of accuracy is perfectly fine. If you want to do more than that, then we have to apply a little bit of domain knowledge. That is, what do we know about the problem? And based on that, how do we make some decisions about what's important and what's not? And if we think about what is important in the Endbody problem, where things interact with gravitational forces, the first thing that I point to you as a hint is the formula F equals G m1 m2 over r squared. G being the gravitational constant, m1 being the mass of body 1, m2 being the mass of body 2, and r being the distance between those two bodies. Okay. This tells us that force is dependent on how close the objects are, in that objects that are closer together have a higher force, and objects that are far apart have relatively little force. And that means that you could estimate forces that are far away without a huge loss of accuracy. In principle, if I drop a whiteboard marker on the floor, the gravitational influence of Jupiter has some impact. Whether it is positive, negative, or zero depends on Jupiter's relative position at the time of my clumsiness, but the effect is so incredibly small that it is worth ignoring. Gravity is, when all is considered, a very weak force compared to other fundamental forces. When you pick up a box off the floor, you are using your muscle strength and defeating the gravitational pull of the entire planet Earth. The ceiling above you is technically pulling up on the box that you are picking up on, but the mass of the ceiling is negligible as compared to the mass of the planet that you are standing on. And so that gives you some idea of just how incredibly weak gravity is as a force, in that you are defeating the whole planet every time you pick something up, and then maybe that provides you motivation for your next gym workout. Take that, gravity. You're not the boss of me. Okay, so there's a range, right? If something is very close by in the Endbody problem, it's important, and we know that it will have an impact on the movement of the bodies in question. If something is really, really, really far away or extremely tiny, then it doesn't have any practical impact and you could ignore it. But what about things that are in the middle? Not close by, but not so far away that you could just totally declare them irrelevant. What can we do about that? We could use an estimate for points that are in that middle distance. Points that are far away, but not absurdly far away, contribute only a small force, and you can estimate them in some crude manner. And our strategy is we will divide the points into bins, and a bin is going to be a cube representing some area of space, and we can compute the center of mass for each bin. And then when calculating the force on a particular particle, you can use the center of mass for bins that are far away, and you can use the individual particles for ones that are close by, and we get a reasonably accurate estimate as a result of this. Right, the ones that are close by have the biggest impact, so we get the big details right, but the ones that are far away have less impact, and computing their center of mass reduces the amount of calculations that we have to do, since we have an average for it. All right, let's give that a try. To put some numbers to this, as they were in the assignment, suppose that space is divided into a cube so that it goes from 0 to 1,000, and we can take bins that are of length 100 and cube-shaped. So there are 1,000 bins, each of which is 100 units on each side. And to increase the accuracy, we would have more bins. And we would perhaps also consider changing what happens with what we consider a bin that's close by, so that more bins are in the area where we do direct calculation and fewer of them are considered far enough away that we use the average. To increase the speed, then we have fewer bins, or we change our definition of what counts as far enough away so that more of the bins are far enough away that we use the average. Okay, so those are some approaches for how we could improve or make our simulation faster, depending on how accurate we want it to be and depending on how fast we want it to be, recognizing that we're trading them off against each other. And so to do this, I have defined some types where we have a point structure, and a point has x, y, and z coordinates, as well as a mass here also being a floating point number. And we're actually going to improve on that a little bit by putting a bin property on there so we know up front what bin a particular point belongs to. And later on, we'll use that to see if something is considered close by. And in my example code, I iterate over each point, so generating its values, and I assign the bin at that point, because why iterate over the collection a second time later, right? If you were reading in points from a file or something like that, you could, again, just as easily calculate what bin they're in at the time when they are being read in. And in this case, because we're randomly generating it, it makes sense. You don't want to iterate over the collection to assign bin numbers a second time if you don't have to. And then what we're going to do is compute all of the masses in parallel. We'll create perhaps one thread per bin and add a point's position if it belongs in the bin, and it parallelizes with the number of bins. That's a strategy for approaching this, and our goal is to save time. So we'll save time while calculating all of the forces. We will compute exact forces for points that are in the same bin and then the directly adjacent bins in each direction. So there will be 27 of those. 6 bins share a square, 12 share an edge, and 8 bins share a point with the center bin. And if there's no adjacent bins or at the edge of the map, we'll just pretend there's no points in the place where the non-existent bin would be. This does increase our overhead. There is going to be a little bit of extra work to doing this, but we'll find out if there is some benefit. So let me walk you through quickly the Endbody code that I wrote. The code is, of course, in the course repository, and we're going to base a number of different examples on this Endbody problem, so it is worth our time to take a little effort to become familiar with it. And this originally started off as the ECE 459 Endbody assignment in C and C++, and that was originally from a GPU GEMS source. And so I'm going to define the number of points here as 100,000. We'll change that as needed when we are looking at what the effects of different modifications we want to make are, and epsilon here is just 1 times 10 to the minus 10. This prevents any risk of a division by 0. You'll see when we do one of the calculations, we'll add epsilon to some things just to make sure that there's no possibility of division by 0, because that, well, makes the math a little nicer and avoids us having to worry about did we accidentally subtract 2 things that end up with 0. Okay, we have our definition of the struct point. As I mentioned, later on we're going to end up adding the bin to it, but this is the original unmodified version in which we do not have that. And I've also implemented the display trait This is analogous to toString in a language like Java, where I've said this is how I want it to be formatted when I'm writing it out to the console, and it does prevent getting some unexpected value. So, okay. And the formatter, I just said write using the macro for a given formatter, and I've made it in parentheses, the X, Y, and Z components, and then the mass following that in square brackets. Okay, I also have a structure acceleration, because that's what we're computing, right? We have the points, and we're going to compute the acceleration on those. If you wanted to take the simulation further than any individual step, what you would do is you would compute the acceleration, then apply it to the point to give the point's next position. We're not going to take it that far, even though it is the obvious next step for having, a simulation that's running the Endbody problem, because at this stage, really all that we are interested in is seeing to it that we have a nice parallelizable problem where we are going to actually parallelize it and see the impact, if any, of applying an optimization like putting things in bins. Okay, and acceleration gets its own formatter as well, because we should have a formatter for it, because that's what we need to print it out nicely. And then we have a function here, body-body interaction, and this one actually calculates the acceleration for a given point. And so it takes a reference to a point, the one that is the current one, the other point, that is the point that is exerting force on the one we're doing the calculations for, as well as a mutable reference to the acceleration structure that is the one representing the current point that we're working on. And so we're going to see later on we have a vector for each of these things, and we need to know, okay, for the current point, here's its acceleration vector. Could you pack them together? Sure, if you wanted. So we're going to calculate the difference as a point. So the current point dot x minus the other point's y, and the current point y minus the other point's y. And same for z. And the mass of this is 1, even though it doesn't matter because we're not going to use that field in the calculation. And we calculate the distance squared as difference is x squared plus y squared plus z squared plus epsilon, again, to prevent any possibility that we have any division by 0. And then we will calculate distance squared times distance squared times distance squared, and then divide 1 by the distance sixth. And then we calculate the magnitude as being the mass times this factor. And then our current acceleration is whatever we started with. We'll initialize it to 0. In the x dimension, it's the difference dot x times the magnitude, and so on and so on. The math on it isn't super exciting, and it's okay if you didn't follow super closely what happens with the body-body interaction math and why this works, but consider it to be correct in your physics calculation. And then we have the calculate forces function, which initializes your acceleration vector, that's shown down below, and then for each point, get the current point from its vector from the initial positions, get the accelerations item for that point, and then for a given point, calculate the force on it from every other point. So for let other point equals this, and it's any other point, and then call body-body interaction with that. This highlights actually why we need the epsilon thing to avoid any sort of division by 0. You could add as a little step here, if I is equal to j, then just skip this one because it's the same point, but not strictly necessary because epsilon helps us out. Okay, initialize position is not anything super interesting. We will use a random number generator and generate a random point which has a random x, a random y, a random z, and a random mass. And the point is generated inside our space somewhere, so it's going to be between 0 and 1000 in all instances, and its mass is going to be between 0.01 and 100. Again, not critical what those values are. We just need some examples and have some things ready. For initialize accelerations, we are just going to create a new vector for the accelerations, and we will initialize it with a new value of everything being 0. All right, then our main function will run. It initializes the positions and prints them out just so you can see what they are, and it calculates the final accelerations by calling calculate forces, as we've seen. So it is pretty straightforward, and we can even run it. It has to compile it first, but I think we can spare a couple seconds. And so it's created all the initial positions. There's a bit of a delay now while it actually computes all the details of what the accelerations are. You probably can't hear it, but the fan in my laptop has started ramping up. Something is happening. Yeah. As I recall, this will take some significant amount of time to actually execute, and that's okay. It is... how it goes. The unmodified version takes about 162 seconds, which is to say it's almost 3 minutes long. Tempting as it would be to just stare at it the whole time, no, I don't think we will. That doesn't seem like a particularly good use of our time, but it is definitely noticeable in how long it takes to actually run it. So we'll call it off here and just go on to looking at the alternative to this, and the alternative to this is the Endbody bins version. Right, we'll look over the modifications that were necessary to get this done. I added in the constants the bin side as 100 and the number of bins as 1000, so that those values are just on hand very easily, and we can make use of those quickly. And to the point structure, I added the bin parameter. It is a usize, so it's an unsigned variable, but it is of size type and not strictly directly an integer. Why is this the case? Because when we want to use something as an array index in Rust, it really wants it to be an unsigned size type and not necessarily just any random integer. And so you can, as we did previously, cast it. You can say, take this integer and make it as usize. However, we could save on that by declaring it to be usize to begin with, which just acknowledges upfront what the type in question really is, and that is fine. It's worth doing. Okay, so the format for point really hasn't changed. We're not going to print the bin on it. You could if you wanted, but we didn't. It has the acceleration has not changed either, and body-body interaction is also the same. Nothing has changed about that, but calculate forces did change. Calculate forces is different now. And we'll see as we go through it what actually happens. We'll come back to this. So we initialize positions and centers of mass, as you would expect, and so we're again going to try to do this all in one go. Instead of having multiple iterations over everything, let's see if we can do it in a quick manner. So initial positions is the same as before, and centers of mass is a new vector. We're going to compute for each bin its center of mass, and as efficiently as we can, we will try to do it all at once, which usually is better than iterating over the collection again. So we generate a random point, and that hasn't changed. and we will ultimately just use this exactly as it was, and we're going to assign the bin using a calculate bin function. The calculate bin function just takes the x and drops the floating point component, so rounds down, and divides it by bin side. So if the x position is 512.7, we round it off at 512, and then we assign it to the bin by dividing it by 100 and its integer division. So we end up telling us, okay, the bin value here is 5. And the bin is calculated as the x bin times 100 plus the y bin times 10 plus the z bin directly as a u size. And again, this is just something, if it seems confusing, you could pen and paper a little bit to work out that actually this produces a reasonable bin number if you interpret it correctly for identifying where the point appears, what bin it's in. So that is going to be how we calculate our bin number for it, and we will assign that value to this point. And then, because we actually know that, we can then add it to the center of mass for that bin. We will do our computation. Bin at this point, x plus equals the point mass times point x, and so on and so on. And in the end, we add the mass to the total mass of the bin. That way, we have, as we've generated each point, put it in its correct bin and computed the center of mass for that bin, and we're happy with that. It saves us a little bit of time later. Once we are done adding all the points and everything, then we actually iterate over the centers of mass again, and as long as that bin is not empty, which could happen when we have 1,000 bins and 100,000 points, there is a non-zero chance that one of them is empty. And it's not likely, but it is not also impossible. So there's a check here that says don't try to do this division if the mass is 0, because then we have a division by 0 error, which we could easily just stumble into. And it would be more obvious if you had fewer points or more bins that this is a potential risk, and therefore better safe than sorry. In any case, then here we can actually divide the x, y, and z components by the mass, which you may have noticed was missing in the previous step, so we don't divide too many times incorrectly. Okay, very good. Initialize accelerations hasn't changed. Great. So back to initializing positions and center of mass. We add all the things into our vectors, and we compute all the centers of masses, and then we return here as a tuple our initial positions and our centers of mass. Good. In our main program, create our initial positions and centers of mass, print them out as needed, and then calculate forces. So let's go there. So calculate forces now takes as our parameters the two vectors that we have. Nothing exciting there. So we're going to iterate over each point. And looking at an individual point, we will fetch the point out of the vector, and we will also get the acceleration that corresponds to it out of the vector. And then for each point j, then we are going to look at, do we need to do anything here? So we get the other point. If the other point's bin is adjacent to our bin, then we do the calculation and we actually compute exact forces for that point. And so adjacent means it's in the same bin as the point that we're looking at, or it's in one that is touching somehow, in which case we do body-body interaction with the current point. Otherwise, we don't do it, we skip it. Okay, let's go on. And then for the point that we're looking at, we also use the center of mass calculation for all non-adjacent bins. And so if the bin that we're looking at is not adjacent to the point in question's bin, then we do body-body interaction with the current point and the center of mass from the faraway bin. And that, in the end, produces our total result. All right, but what about is adjacent? How do we determine that? Okay, if you've looked at the code already, you'll have seen this, and you might have seen me scroll away from it quickly when we saw it. Not the ideal case, how this is written, but you'll see it actually made a significant difference in performance when I changed it. So what I originally wanted to do was make the adjacency vector be this, as 27 adjacent bins of I32. So that actually wasn't great. Originally I wrote it to use the adjacency vector and iterate and add its current index and return true, but it was very much slower than the approach that I actually wrote now, because I looked at it using a profiling tool. We'll talk about profiling tools later, of course, and the profile told me that a ton of time was being spent in generating slices for the comparison, suggesting that actually the approach that I was going for required creating and destroying a lot of the slices structures, and it would be better if we didn't do that. So we don't. Instead, there is a horrifying if condition with all the OR operators on here. And if bin 1 is the same as bin 2, or it's the same as bin 2 plus 1 and everything, and you calculate the adjacency vector, if you're me, by breaking down and using a paper diagram to say, all right, well, if it's plus 1 in the x direction, then that's like plus 100. But if it's plus 1 in the x direction and minus 1 in the y direction, and plus 1 in the z direction, then you end up with 91, because of our earlier definition where we said, okay, it's x times 100 and y times 10 and the z as it is, to produce all of the possible permutations in this vector. I mean, that's how I did it originally. Then I had to rewrite it as the giant if-else block, which sucked, but okay. The things we do for performance. I mean, I wrote it so that it's, if this, return true, else false. Just for clarity of reading, you can return an if statement directly in this case, and you could just put return instead of if here on line 161 and skip the rest of it. Doesn't matter too much. So that's the adjacency vector calculation, and that's how we determine if a point is adjacent or not. And if it is, then we'll take it as it is, and if it's not, then we use the center of mass belonging to that bin. The idea being, of course, that we save time, right? The number of invocations of body-body interaction in this scenario goes down. Body-body interaction itself is not a huge function. It's not a lot of lines, and none of the individual steps here are super complicated. However, if we're going to do this a lot of times, that cost adds up. Add to it also the function call overhead for calling body-body interaction. And so if we do it only for points that are close by, and then once per bin for of the 1,000 bins, so every other bin other than the 27 adjacent ones, that reduces in a significant way the number of invocations of body-body interaction, which will hopefully reduce the total runtime of your program. Now, with 100,000 points, the modified version takes about 147 seconds, which is about 15 seconds faster than the previous one. With 50,000 points, the original Endbody program takes about 39 seconds, and the optimized about 37. We are forced, I think, to acknowledge that there is additional overhead added by computing all of the centers of mass. So you have to have the bins calculated, and you are computing the centers of mass, and there is some extra work doing that. And it looks like, anyway, that there is some benefit to this when we run it. If we have 50,000 points or 100,000 points, it does seem to make a difference. I mean, it's not a huge, dramatic difference, but it does apparently matter. Of course, parallelizing this actually matters more. If I just parallelize without approximations using the Rayon parallel iterator, which we're going to talk about very shortly in an upcoming topic, that actually gets the execution time for 100,000 points down to about 25 seconds. So parallelizing the problem has a much greater effect on the trade-off of accuracy for time, but of course what we accomplish in one thread could potentially be scaled out to all of the threads. So if we combine parallelization and bins, that might produce the best output. And just thinking about it in general, right? Every bit helps. If you have something that you can't parallelize for some reason, the approximation might be helpful. Or if you can parallelize it, then approximations might improve the parallel version. And so at any time where we could skip doing unnecessary work feels like winning, so to speak. Another thing that we'll talk about is just very briefly loop perforation. And it's a little bit like early phase termination in that it's in sequential programs throwing away information that is not useful. And what it says is that if your data pattern is somewhat regular, like it is here, instead of a loop where you iterate over each element of the loop, you could skip every second element of it and then add a little adjustment factor at the end. And this reduces by about half the amount of computation that you actually need to do, assuming that the numbers array is nice. And this kind of thing works in video encoding, that you can drop some details because you can interpolate the details in between, or the differences between two frames are really not that stark, so it's possible to actually just save on the amount of space that you're using by storing less data or compressing data more without any significant drop in quality. And if you do this right in your video encoding, nobody notices that the encoding of your video is worse, but it saves space, which people definitely notice, especially if you are on the streaming service and you are streaming this video to somebody who's watching it. Anything you could do that reduces the amount of data that you're streaming to them is in some very direct sense saving your company money, because paying for bandwidth is sometimes a thing, especially if you are Netflix and you are consuming quite a lot of it. And by that same token, if you are watching this video and you are seeing it on a not great connection, then anything that compresses it so that your video is not using as much bandwidth is probably of benefit to you, because again, your connection is not great, and you need to make the most of what you have. So loop perforation also works for a couple of other things. You could use it on evaluating forces on water molecules, something not too different from the Endbody problem, except in this case a slightly different problem domain. It also can work on option pricing in financial simulation. We could use it in video encoding. If you change the loop increments in a video encoding example from skipping 4 to 8 in your loop, it gives a speed up of about 1.67 and decreases your signal to noise by about 0.87%. And increases your bit rate, so how much data you're getting through on actually watching this video, by about 18.5%, and ultimately is not easy to distinguish for the user who is watching the video at the other end. Indistinguishable is, of course, perhaps a matter of taste.